Hey everyone, welcome to Office Hours with Professor Eric. This is for December 15th, 2025. In this quick video, I'm going to walk you through two must-have tools to view S parameters in the time domain, the frequency domain, as single-ended and as differential or mixed mode. If you want all the details and if you want links to all the tools, as well as a link to download some sample S parameter files that I'm providing you, be sure to check out my Substack column for December 15th, 2025. You can click on the link that's in the show notes. You can also use the QR code over here on the bottom right of the screen. Well, let's get started. I want to show you the first tool, which is from Teledyne LaCroix. This is the WavePulsar Xi. It's the user interface to their network analyzer. It's part of the Maui Studio software package. You can use this link to download it from their website, and I'm going to walk you through step by step how to install it and how to run it so you can view the S parameters of a file in single-ended, differential, or time or frequency domain. Here's the website link. You're going to go to download the Maui Studio software. It's completely free, but it does require you to register. I have an account set up. It's completely free. So you set up an account, say log in, and now you're asked to continue. And now it automatically downloads the Maui software for you. So this is what you're going to download, the executable. And after it's downloaded and you run it, we continue with the dialog box, we accept the user agreement, and now we're given this screen where we can select what we want to install. The only part of Maui Studio that we need for the S parameter viewer is the WavePulsar. So we click that box and we say install, and then it will go through and install the WavePulsar Xi user interface. And that's it. That's the installation process. When we double click and run the WavePulsar 40iX software for the first time, it takes about 20 seconds to load, and then we get the dialog box that says no WavePulsar hardware detected, running in standalone mode. That's exactly what we want. We say OK, and it opens up the user interface. And this is what we end up with. Now, depending on in my case, I've run this before, and so the window that comes up remembers how I left it. But if you have installed it for the first time, you're not going to see the same data that I have here. Instead, you're going to see a blank screen, and you're going to come over here to File, and you're going to call, and you're going to pull it down and go to Recall Touchstone. And that opens up this window and gives you an opportunity down here in order to select the file. So I'm going to say open up the file. And there's another dialog box that opens that allows you to browse through the menus, and I have these S parameter files. I provided a link to these S parameter files so you can download these same files if you're interested, if you have your if you don't have your own S parameters to take a look at. So go back to my Substack Office Hours post, and you can click on the link to download these S parameter files. And I have a variety of both 2-port and 4-port S parameters in this list. So for now, we're actually going to do a 4-port. So let's grab this one that has the connectors on it. Again, you can browse through these at your leisure. This is a differential pair with a board-to-board connector in the middle. I'm going to click on it and highlight it, and then I'm going to come down here and I'm going to say open. And now I've got that file loaded, and here it is. The first step is selecting the windows that we want. And under display, we have a couple different options. Depending on what I'm doing, I like to use, and this is all personal preference only, but my best practice is I like to use the tandem. So I use frequency domain on the left side, time domain on the right side. But if you want to keep separate the insertion return loss from the crosstalk terms, for example, then I also like using the Quattro grid. So the first step is we open up the grid that we want. The next step is we select what we want in each grid. There are a total of 16 different registers that we can use to select any of the S parameters that we want to display in whatever format. They're all interchangeable. My own personal preference, I like to do the frequency domain on the left, time domain on the right, and the insertion return loss up above, crosstalk down below. And so I'm going to select a S11, S21, 31, and 41. Those are going to give me the columns. I have the check mark here, and I can select which aspect of those terms I want. This is going to give me the magnitude in dB. I have these other terms, and then for time domain I could use the step response or the impedance response. So for now we're going to use the dB response over here. Now this is kind of a jumbled mess, and to organize it, to move things around, here's what we're going to do. I'm going to put insertion return loss up here, crosstalk terms here, and I'm going to do the time domain over here. And to do that, all we do is we grab the little icon box and we drag it over to the cell that the display that we want it to be in. Let's see, I want these guys in here, and then I want TDR over here. This is another TDR, this is another TDR, and I want crosstalk down here. And so in about 10 seconds I've organized all the data in a way that makes some sense. And over here on the right hand side I've selected these S parameter terms and I selected the impedance. This is going to be the TDR plot, and so I'll be able to plot impedance versus time. So after we've set up the display, after we've selected which S parameters we want to display, the last piece is for the time domain. I want to adjust some of the features. So I'm going to come to configure, and here's where I can adjust the rise time. You want a rise time that is short enough to give you the resolution you want, but not too short that will give you Gibbs ringing artifact. And so my rule of thumb is you look at the highest frequency component that's you have good data at, 1 over that should be the rise time. So even though I have measurements to 40 gigahertz, the SMA cable craps out around the 20 gigahertz range, and so I'm going to set this for 1 over 20 gigahertz or 50 picoseconds. I like upsampling that does a little bit of interpolation, makes smoother plots, and I want to display the round trip time, and I want to apply this to all of the S parameter terms. Now we're done. And then lastly, I want to adjust the scales. And to do the scales is really easy. I find a plot that is in one of the grids that I want to change, like for example, the insertion loss. Let's see, that's I have insertion return loss over here. So here is the return loss. Once I click the icon box down here, you'll notice the scale settings over here change. So if I go to R2, then I've got the R2 settings. If I go to register 11, it changes here. So let's go back to register 1. I like the frequency range, but in terms of the vertical scale, I want to start at 0 and I want to end at minus 40. So I want to start it at 0 and I want to finish at minus, and now I've adjusted the scale. Now in this particular setup, each of the traces that I'm plotting are separate and distinct, and I can have them on different scales. If I want them on the same scale, I have to kind of link the scales, and the way we do that is we come over here to utilities, we come to preferences, and we come over here to zoom join preferences, and so if we want them all to be linked together, then I'm going to do join all, and you have some options here of which ones we can do, and I'm going to say join all. That means whatever I have plotted in the time domain, all the scales will be the same. Whatever I've plotted in the frequency domain, all the scales will be the same. Now I can come back over here, and now let's see, I have top is 0, bottom is 40, and I want to change that for this one here. So I'm going to go to top is 0, bottom is minus 40. And now let's change them for all the scales. And so you can see that for any of the S parameters, they're all the same scale. This is a convenient setting that I like. And now we can take a look at the S parameters. This is single-ended. Here's my insertion loss. Looks like an insertion loss. Here's my return loss. Boy, pretty darn good return loss. Here is the near. This is the near and the far end crosstalk. This is in the frequency domain, and I can do the same thing looking at it in the time domain. Here is the impedance, and let's see. I can see that. Let's check the impedance plot. So here is the first one. Let's see, 0 and 5. That looks good, to 2 nanoseconds. If I wanted to change the scale, I can make this 10 ohms per division, and because I linked them all, they all have the same scale change. And when I look at these, I see, let's go back to the 5, and I also have the time base here on 2 nanoseconds. Let me go to 5 nanoseconds just so I can see the ends of these guys. And okay, maybe everything ends at 2 nanoseconds. So let's go back to 2 nanoseconds. Let's see. And so what I see is here is some uniform traces. They're not all the same impedance in this example. Here's a launch of the connector for a couple of the pins. Here's the connector region. Here's the launch on the other side of the connector, and here's the daughter card on the other side of the connector. And so I can read the impedance right off the front screen here. They're within about plus or minus 2 ohms, 1.5 ohms of each other. And here is the crosstalk. Let's see. This is the near end crosstalk. Now, orange is not too distinct from red, so let me change the color of register R13. That's this guy here. I'm going to make him a yellow. And let's see what that looks. There he is. Nice bright yellow. This is the near end crosstalk. I'm going to change this scale also to 25 millivolts per division. That means I'm sending 1 volt in, and this is the crosstalk. And you can see that, okay, I'm getting, this is, if it's 1 volt in, 50 millivolts is 1%. So this is very little crosstalk between the connector region. There's no crosstalk at all in the board level region and just a little bit in the connector region. These are single-ended signals. And here is the far end crosstalk on the same scale. So here it is on the 25 millivolts per division scale. And just as you'd expect, we see the far end crosstalk with a little dip here. These are mostly strip line structures, and so you can see here there's no crosstalk in the region of the uniform lines. All the crosstalk is happening at the connector. So this is looking at the single-ended S parameters of this file. If I want to look at the differential S parameters, then I want to convert the single-ended to differential. And here's how I do that. And before I do that, make a note here that an insertion loss is S21. So that tells me what the connectivity is. It's port 1 goes to 2, 3 goes to 4. And we're going to use that when we do the conversion. So I'm going to come here to convert. It opens up this dialog box that allows me to set up the ports. So this is my Touchstone file ports, and this is how I want to configure the differential ports. So this is going to be the differential or mixed mode S parameters, and sure enough, port 1 is going to be the differential port 1, port 2 is differential port 2, and 3 is going to be the common port 1, and 4 is the common port 2. This is rarely going to change. This is the standard convention. But this is what's going to change. Let's see. It's port 1 is on the plus side, but it's port 3 that goes to the P side in the front of the transmission line, and it's port 2 that goes to the back end, and port 4 on the other end. And that's why we have 1 goes to 2 and 3 goes to 4. Now that we've got the port assignment correct, now we close the box, and it says you want to save the changes. Yes, I do. And those single-ended S parameters are all going to be converted to differential S parameters. And the way we do that conversion is we come over here and we click recalculate. And it's going to say, yeah, I don't have all the information I need. That's okay. And I'm going to say okay. And now it's going to do that recalculation for me. And look, now I'm plotting, instead of the single-ended S parameters, I've got the differential S parameters. And so let's change what we want to plot. I want to plot SDD11. That's going to be in R1 and R2. Okay, that's the same. So I have the differential insertion loss and the differential return loss. And then we can look at we could do a variety of combinations here. We could do this as the common S parameter. So here's the common return, and here's the common insertion loss. And sure enough, it looks like a insertion loss, looks like a return loss. Alternatively, we can also look at the mode conversion terms. So here's an SCC11 and an SCC21. And sure enough, not a lot of mode conversion over here. And for the TDR response, let's see, we were looking at single-ended before. Let's look at the differential. So let's SDD, SDD, and let's do the common. And let's look at just these two. And let's turn off the common. And so here's that differential return loss. And you can see that that I have a slightly different impedance from the two sides of the board. That the impedance of the line on one side of the board, the differential impedance, is pretty darn close to 100 ohms. The other side is a little higher. So the board isn't really symmetric. There are two different daughter cards that are connected together. But in the region where the connector is, oh my gosh, what a beautiful 100 ohm differential impedance connector that I've got here. And then over here we can look at mode conversion if we would like, or we could look at I rarely look at the common return loss. I rarely look at the common signal TDR, so we can look at the mode conversion term. So here is the reflected mode conversion term, and I'm going to use the step response for that. I'm going to use the step response for the transmitted mode conversion term. And so here is the transmitted mode conversion term. We'll turn these off. We'll select step over here. And let's move that over here and this one over here. And now we can see the reflected mode conversion. So there is a little bit of asymmetry at the connector launches. And here is the common signal that is transmitted through the interconnect. And we can see that because of time delay asymmetries in the P and the N line, from somewhere we're getting some mode conversion. Not a lot, but in fact this says about 15 dB mode conversion, and this says about 50-60 millivolts out of 1 volt. That's roughly 5 to 6% of the signal comes out as common signal at the far end. So in this way, we can import a single-ended S-parameter file, display it in the time domain, the frequency domain as single-ended, or convert it to mixed mode and look at the mixed mode S-parameters in the frequency or the time domain. It's an incredibly simple to use, easy, versatile tool, completely free to download. So try it out and take a look at some of the sample S-parameter files that I provided, and you can explore some of their properties. Now in this video and in this office hours, I'm not talking about how to interpret the S-parameters. I have links in the office hours on some tutorials I've done on how to interpret the S-parameters. In this video, I'm just showing you how to use this tool to open up and view the S-parameters. Interpreting them, once we've opened up the tool, interpreting them is the most important thing that we want to do, and that's where you're going to want to go back to my office hours post, take a look at some of the links to the webinars and the tutorial videos that I've provided there on how to interpret S-parameters. And if you want to become an expert in signal integrity, understanding S-parameters is critically important. You want to view those webinars, and then you'll be in a position to take advantage of these S-parameter viewing tools in order to explore what's contained inside the S-parameter behavioral model of interconnects. Here's the second S-parameter tool that I think is useful to know and you should have available to you. And it's for a Korean company. The tool is SNP View. It's only available online, and here's the link to download it. And so when we click on the link, it brings up the website. Here is snpview.com, and this is where we can import the S-parameter files. There are a few quirks in this tool that I think are important to pay attention to. Now, this is one of those situations where if you already know about S-parameters and know what to expect, you can reverse engineer what the tool does. And I've spent a couple hours with this tool trying to understand the details of what it does, and I'm going to try to explain those details. The first nuance that it has is the ability to import both S2P and S4P files. The way it distinguishes the two is in this definition over here. Single means an S2P file. Differential translates to, oh, it's an S4P file. And once it is in an S4P file, so for example, we click differential, we're going to import an S4P file, and then we can display it as single-ended if this box is unchecked, or if we check that box, we display it as differential S parameters. So that's how we're going to distinguish importing S2P files or S4P files and distinguish single-ended or differential or mixed mode S parameters. The second part that we want to be able to evaluate is looking at the S parameters in the frequency domain or the time domain. The default setup is the frequency domain, and that's where we select the options over here of how we want to display the data in what format, either as magnitude in dB or real and imaginary in the phase and all the others. The other way we can display the data is in the time domain, and that's where we can click these boxes over here to select to display the data in the time domain. And so depending on the setup of either it's a S2P or S4P, single-ended or differential, that will change the contextual menus over here. When it comes to plotting, here are the nuances. And to illustrate them, we're going to import an S parameter file. Now, if you don't already have an S parameter file you want to take a look at, you can return to my office hours for December 15, 2025 on my Substack site. There's a link in this post to download a variety of S parameter files that I'm offering you that I use pretty often. So in this example, we're only going to look at the S4P files. S2P follows that path perfectly, and it's a little bit easier. So we're going to look at differential. Once we identify, okay, it's an S4P file, we're going to click the Load File button over here, and that opens up the browser in order to find those S parameter files. And so here are those S parameter files that I've posted on the Substack blog, on the Substack post that you can access. And we're going to grab, let's do this differential pair tightly coupled. This is an S4P. So I'm going to click on this to highlight it. And now we're given this dialog box to select the ports. This is one of the confusing aspects of this tool. This tool assumes that when it converts single-ended to differential or mixed mode, that the port assignment is 1 goes to 3, 2 goes to 4. And so when you are selecting the port assignments for your file, you have to know how it's set up. I'm going to start out looking at single-ended. And as single-ended, I'm going to keep the matched port assignment here of 1 and 1, 3 and 3, 2 and 2, 4 and 4. And we're going to look at single-ended. This mapping of the ports means that when we look at an S21 with this tool, it corresponds to the S21 of our data in the Touchstone file. So we're going to start out like that, looking at single-ended. Everything else is going to be default. I'm going to say OK. I've unchecked the box over here, so we're not looking at mixed mode right now. Let's look at the insertion loss and return loss. So we're going to look at it in magnitude and dB. Let's see, I want to look at S11 and I'm going to look at S11 first. So I've selected that particular matrix element. Again, this is going to be single-ended, and I want to create a new chart. And to do that, we're going to select over here Chart Plot Plus. So I'm going to click that, and it's automatically going to generate a new chart. Now, unfortunately, there's a lot of confusion in the labeling scheme they use. Chart plot is a window in which we can have multiple traces, but a chart itself is the individual trace. So the big blue button over here generates a new window, and in that window we can plot similar kind of functions. For example, this is S11, and it kind of looks like an S11 for this file. Let's plot S21, and I think that is an insertion loss because I remember how I created the files. And so let's look at an S21. So let's see, this is going to be S21 is going to be the matrix element, and I want to add it to this plot. And to do that, I'm going to come over here to add chart. So add chart means add a trace to the plot window that's open up. And so I'm going to say, okay, add chart. And there it is. And sure enough, that looks like an insertion loss. Now the scaling is a little bit funny. If I click over here at the very top, I get the top setting. I want that to be 0 dB. So I'm going to literally just type in 0 there, and now it's going to rescale it. And I can move it up and down a little bit. It's kind of locked in place here, but I can move it down and shift it a little bit. But to change the scale, I can click the top one over here. I can click the bottom over here as well. Now I'm plotting my two S parameters. The blue is S21 and the red is S11, looking exactly like I expect to see. And while we're here, let's add the near end crosstalk S31. So here's 3.1. Let's add that as a new chart, and S41. And let's see, here is 4.1, and we'll add that one in as well. And I have to go in here and it readjusted the chart. I'm going to make that 0 at the top. I like nice even numbers here along the vertical scale. And so here is the S parameters in that file. If I wanted to change a color, like, for example, S21 that's blue, maybe the orange is too close to red. What are my choices? So let's see, the orange, you can see over here, it says S31. Here's the orange S31. I'm going to right mouse click in the tab over here, and now I can change it. Let's see, what's a better color? Oh, I think I like purple. Let's try purple, and there is the purple. So we can adjust the features of any one of the plots that are within this chart plot altogether. And this is how we can look at the S parameters for the single-ended file. The next thing we're going to do is look at the TDR response of some of the return losses. And to do that, we're going to come over here and we're going to click the TDR button. And you can see immediately when I click TDR, these changed. And I have access to the return losses for each of the ports. So let's create a new chart window to look at TDR. So here is my S11. I'm going to create a new chart plot for S11. Takes a little bit of calculating over here to do that conversion from the frequency to the time domain, and here is my step response. Now I have a few options that I can use to set up that TDR. If I come down here to TDR Advanced Options, let's see, I can change the rise time, a few other little things like delay, and a few other things that aren't so important. But I'm going to keep it at 50 picoseconds. So it uses 50 picoseconds as kind of default. Depending on what the highest frequency is, 1 over that should be the shortest rise time that we use. Again, even though there's 40 gigahertz data in here because the SMA connectors, I think 20 gig is the highest bandwidth of usable data. 1 over 20 is 50 picoseconds. So I'm going to use that. If I wanted to evaluate what is the TDR response of this interconnect. This is the return loss here. If I want to look at what's the return loss, if I use not 50 picoseconds, but let's try 200 picoseconds, I make the change over here. I've changed this. I have to add a new chart. So I'm going to come over here to add a new chart. It's going to do some calculations, total of about 10 seconds to do the calculations. And here it is in blue. Now, it'd be nice to zoom in on this. And so to do that, the way to change the scales really easily is I'm going to zoom in on the horizontal axis. So I'm going to start on one end, I'm going to click and hold and drag it across, and now I open up this window that I'm going to zoom out on. And so I release, and now I've zoomed in. And now you can see the impact of the TDR response by changing the rise time. Here's that very sharp discontinuity, large inductive discontinuity at a 50 picosecond rise time. And you can see with a longer rise time, it's smeared out quite a bit more. Uniform part of the line here. And you can see here we're reading, wow, pretty darn close to 50 ohms. This is a pretty darn good match to 50 ohm single-ended impedance lines. And then of course at the far end, that's where the other connector is. And you can read the other details about each of these different plots over here. This is, the very top line here is the rise time. Here it is at 50 picoseconds on the red one, and here it is 200 picoseconds at the blue trace over here. And so that's how we can look at single-ended S parameters in the time and frequency domain. Now let's take a look at the differential response. And here's where it's important to remember that the insertion loss, the way we have the ports mapped, is S21 in our Touchstone file. So if we want to look at the insertion loss, we're going to go to mix mode, and we have to change that port assignment. And to do that, we can click the edit box over here. And now we have to be careful about the port assignments, because what this tool is looking for is an insertion loss being 1 to 3, 2 to 4. Now these numbers on the outside are the numbers that the tool is using to plot its S parameters. These are the ports that it thinks the connection is for the interconnects. But in reality, we have 1 to 2, 3 to 4, and so we need to change the port assignment from the Touchstone ports that are in our Touchstone file to what the tool is expecting for a going in and a coming out port. And to do that, we first reset these two that we're going to change, and now we're going to go 1 goes to 2, 3 goes to 4. The port assignment in our file is 1 to 2, 3 to 4, and so that means that in our Touchstone file, an insertion loss is an S21. But this tool is looking for an insertion loss being S31. And so we have to do this port remapping. So now this is an insertion loss, an S31 and an S42. Now that we have the port assignment correct, now we can say OK. And now, because we have clicked this box of mixed mode, we've taken those S parameters from our file, done a little bit of matrix math, converted them to mixed mode S parameters, and now they're available to us. So we're going to come up here and we're going to create a new chart plot for the differential S parameters. So let's see. And I want that in dB. And so we're going to come over here. We're going to select dB, and I want to plot an SDD S21. So now let's add a new chart plot. And here it is. This is the differential insertion loss. Now over here we had the single-ended insertion loss, and we could add the differential insertion loss to this plot. So we say add the chart, and now you can see that yellow, let's see, that is the differential insertion loss, SDD21, and we can compare it to the S21. Now, it's kind of cluttered here. I've got a lot of data. I want to get rid of some of these. So let's get rid of, let's see, S31, that's purple. I'm going to delete that. And let's see, let's get rid of S41, that's green, that's this one. And you know what, let's get rid of the return loss, S11, and that is red. So here we're just plotting the single-ended S21 in blue, and in yellow is the SDD21. In fact, let's change the yellow to maybe a nice red. And so now we can have a clear distinction between the differential insertion loss and the single-ended insertion loss. Because of the coupling between the two lines, they're not the same. And if I want to, again, change the vertical scale, I'm going to make this 0 at the top, and there we go. So we're able to convert the single-ended S parameters into mixed mode. We're able to plot any of the mixed mode S parameters. Let's look at the differential return loss, S11, SDD11. We'll add that to this chart over here. This is add to the chart, and there is the differential return loss. And in the same way, we can look at the differential TDR response. So we're going to click to TDR, and this is the DD or CC are the only two options that we have. So look at the SDD11, the differential return loss, and we need to open up another chart window that is defined for TDR response. So I'm going to open up a new one over here. It's going to do the calculation using the mixed mode S parameters, and here it is. This is the interconnect that I've got. I want to zoom in on this region. I click and expand about it, and now here's my differential return loss for that trace. I can look at it from the other end as well. I'm going to click S22DD, so this is going to be the differential return loss from the other differential port. I'm going to add it to this chart, add it chart, and it's going to do the calculations, and here it is. And again, I want to zoom in on just this region, and you can see that, oh my gosh, they are virtually identical. Not exactly the same, but really, really close. This is a very symmetrical line with about a 91, in fact here it is, 91, 92 ohm differential impedance for the region of the line. And then finally, we're going to take a look at another file and look at its insertion loss and then look at an eye diagram. So we're going to look at this particular file that is an S4P that is part of a backplane trace. So we're going to open that up. The port assignment, I remember, is S1 to 2 and 3 to 4. And we say OK. We're looking at the mixed mode S parameters, and we want to plot the insertion loss. So that's going to be in dB. We're going to do an S21, and here it is as the differential S21, because we know what that should be. So let's add that as a plot, and sure enough, there is our differential insertion loss. Pretty monotonic, looking pretty good. And now we're going to look at an eye diagram through this interconnect. And roughly just looking at it, here's minus 10 dB. It's happening around 4 gigahertz. That tells me that 8 gigabits per second is probably going to be the highest data rate before that eye closes. So let's take a look at the eye diagram at 8 gigabits per second. So we're going to set up eye diagram. We're going to change that to 8. Everything else is going to use just the default. It's going to be on a new chart. And we're going to do those calculations here. Takes about 20 seconds or so to do the calculation for the eye diagram. And sure enough, here is our eye. It's looking not too bad at 8 gigabits per second. I think if I went to 10 gigabits per second, it would probably be pretty closed. So let's just try that. Look at 10 gigabits per second. And let's do that. We can't add it to this chart. We don't have that option. We're going to do another chart plot. And sure enough, pretty darn close. Not a lot of opening here. Certainly would pass. It would certainly fail any a reasonable mask that we would have. So this is a quick walkthrough of this particular tool, the SNP View. It's a really easy tool to use. Couple of nuances to be aware of: the port labeling scheme of what it's expecting, how to convert between singleted and mixed mode, and how to go back and forth between the frequency domain, selecting these options, the time domain, selecting TDR or TDT, and the eye diagram as an extra bonus feature. And then when we create a new window for a chart, we use the chart plot, and within that chart plot we can add additional traces if it's appropriate using the other option of add a chart over here. The advantage is it's a completely free online tool. The disadvantage is it's online, and so that means there's potential security issues when you share your S parameter files online. I find these two tools, the WavePulsar IX user interface and SNP View, are the simplest to use, most versatile tools that I've come across, and I recommend all engineers use one of these on their desktop whenever you want to look at an S parameter file. Using these two tools, there's absolutely no excuse you have to not open up every S parameter file that you get, take a look at it, and see what valuable information it's telling you.